All right, hopefully you've had a chance to listen to the notes on the section and read the section and look at the examples. So let's do a few examples together. I'm going to focus on examples about monotone, bounded, converging, and diverging because I think those are the newer concepts, and then we'll practice everything in class. So here we've got a choice of 4 sequences in my beautiful handwriting. So the first one is S sub n equals 10 minus 1 over n. The second one is S sub n equals 10n plus 1 all over n. And then we have the terms are represented by cosine of n, and then the terms are ln of n. And the questions here is for n bigger than or equal to 1, which of these sequences are monotone and bounded? So we know that we're looking for monotone, which means they have to always be going increasing or decreasing. And bounded, meaning they also have some sort of bound, either upper and lower numbers that they're stuck in between. So we want to see which of these sequences are monotone and bounded. So what I would suggest you do first is pause and write each of these sequences out, the first 3 to 4 terms for each sequence, and kind of make a hypothesis, and then see if you can justify your hypothesis. Welcome back. Hopefully you guys have written these down. The first few terms here should be 9. And when I plug in 2, I'm going to get 9.5. When I plug in 3, 10 minus a third is going to be 9 2/3. And it looks like these numbers keep going up and up and up and up, right? And in fact, I can sort of think about this when I take a limit here, right? If I look at this expression, remember to be bounded is to have a certain bounds, a range. I look at as n gets bigger and bigger and bigger, this number, 1 over n, the smallest it can possibly be is going to be approaching 0. As n gets infinitely large, this will get closer and closer to 0. It will never be 0, and it will never be negative. So the biggest answer I can get here is 10. Similarly, since n has to be bigger than or equal to 1, the most I can subtract from 10 is 1. So this number is going to be stuck in between 9 and 10. And every time the numbers get bigger, because I keep subtracting more and more and more. So I keep subtracting less and less and less. That made no sense. So the less I subtract, the bigger my number is. So I'm starting with 9, 10 take away 1. And I keep taking away, but I keep taking away a little bit less. So every time the number gets bigger and bigger and bigger. So this one is in fact, so we'll highlight this one. So number 1 definitely is monotone because it continues to increase, and it's bounded because it's stuck in between 9 and 10. Remember from our theorem, since it's monotone and bounded, that does mean that it converges. So this sequence would be converging to 10, and we'll learn more about that in class. We'll look at those proofs tomorrow. Let's go ahead and look now at number 2. Number 2 is 10 to the n plus 1. Again, hopefully you guys took the time to fill this in. If you look at this really, really carefully, this is almost the same as number 1, right? If I distribute the divide by n, this is the same as saying 10 plus 1 over n. So in this case, when n starts at 1, I start at 11. Sorry, when n is at 1, yes, I should start at 11. And then I'm going to keep adding, but I'm going to keep adding a little bit less, right? When n is 2, that's going to be 10.5. When n is 3, it's 10 1/3. When n is 100, right, it's 10 100th. So I can see that this keeps getting smaller and smaller and smaller. And because I'm adding to it, but I'm adding smaller and smaller and smaller amounts. As n gets bigger, what I'm adding is getting smaller. So this is a monotone sequence because it's decreasing. And it is also bounded because it's stuck between 11 and 10. 11 is the maximum and 10 is the minimum. So this one is also monotone and bounded, right? This one happens, number 1 happens to be monotone increasing. Number 2 is monotone decreasing. When I look at number 3, when I keep plugging in the numbers, which hopefully you guys already did, we get cosine of 1, cosine of 2, cosine of 3. And if you start using your calculator, this is going to be, 0.54, negative 0.42, negative 0.99. If we think a little bit about what the cosine graph looks like, right? And I drew this one as a continuous graph, but our sequence would have, the points along this. As I take the cosine of 1 is going to be here. Cosine of 3 is pretty close to pi, -1. My numbers are going to keep bouncing up and down somewhere between 1 and -1. So this function, this sequence, is going to be bounded because my terms in my sequence will always be between 1 and -1, but it's not monotone because it does not always increase or decrease. It's going to start decreasing and then they're going to increase and decrease and increase. So although it's bounded, it is not monotone, which means by our theorem it will not converge. And number 4 is monotone because ln keeps increasing. Again, if you wrote these out, you have ln of 1, which is 0, ln of 2, ln of 3, this is getting closer to 1, ln of 4. And again, I would look at the graph, right? So if you have, here's going to be ln of 1 starting at 0, and ln is going to go like this. Because it's very concave down, students are tempted to think that it's bounded. ln is in fact not bounded. As n goes to infinity, my answers here will go to infinity. It's true that it's very concave down. The rate of change is starts to get very, very slow, and it will get to infinity very, very slowly, but it's not bounded. There is no upper bound. There's no maximum value for ln. ln will increase to infinity. So although this is monotone, because it definitely continues to increase, each term is bigger than the previous, it is not bounded. So again, this one is not convergent. So that's kind of leading us into our theorem that both of those attributes are needed for a sequence to converge. So the final answer here is just choices 1 and 2 were both monotone and bounded, which means, by the way, that they will converge, whereas choice 3 is bounded only, not monotone, and choice 4 is monotone only and not bounded. Let's look at one more example where we're actually asking the question now, which of these converge? So now we're looking at, again, 4 different sequences, and we want to know which of them converges. Remember that being monotone and bounded is not the only way a sequence can converge. We can look at the limit. So if I look at number 1, we'll do these ones kind of intuitively, as if I look at the limits here. So for number 1, I have the limit as n goes to infinity, and remember n are positive integers, cosine n over n. So I can look at each piece separately. Notice the denominator is going to zoom to infinity, and the numerator is going to be stuck between 1 and -1, right? We know the cosine of n is going to be stuck between 1 and -1, and the denominator is going to go to infinity. So if my numerator stays between 1 and -1, when my denominator zooms up to infinity, this is going to have a limit of 0. So choice number 1 definitely does in fact converge. It converges specifically to 0. Choice number 2 again goes to using our limits, right? We know that cosine in general is bounded, but this one is not going to be monotone. However, if I look at the limit, this will still converge because the limit of this, if you guys remember from compositions of functions and limits, which again, if you need review on limits, you're going to go to 1.8. I can pull the limit inside because that's where my n is. So as n goes to infinity, 1 over n goes to 0. So the limit of this is equal to the cosine of 0, which is 1. So number 2 also converges. It converges specifically to 1. So going back here, we'll highlight number 2. Number 2 converges, and it converges to 1. 3 and 4 are classic examples for us to use L'Hopital's rule. 3 was the terms of the sequence that looked like n times e to the negative n. We can also use our facts. If I look at the e to the negative n, I realize that this is e to the negative 1 to the n, and e to the negative 1 is a number less than 1. So this thing definitely converges, right? Kind of as an aside, I know that this part by itself would converge. The question is what happens when I multiply the n times it? So I would look at the limit. So the limit as n goes to infinity, I can rewrite this as n over e to the n. Now we have infinity over infinity. So by L'Hopital's rule, this is going to be the limit as n goes to infinity of 1 over e to the n, which is 0. So choice 3 also converges, and it converges specifically to 0. And we found that out by taking limits. Basically, these are functioning as functions, so we're using all the same rules we used on functions. They're just integer-valued functions instead of real-valued functions. But notice we're applying all the same rules. Number 4 is going to diverge. I will let you do the work for L'Hopital's rule, but instinctively we should know what diverge is, because if n divided by, right, notice these are reciprocals. If n divided by e to the n converges, that essentially means that e to the n is the dominant function. So if e to the n is the dominant function, number 4 should diverge towards infinity. If you're not sure, you should compute that one on your own. So for tomorrow, when we start class, we'll start right away working on some practice problems from 9.1 and looking at 9.2.